So my name is Utsav Sethi, and I'll be presenting a study that we did on task cancellation in software. So I'll start by saying that cancel is an important functionality in modern distributed and concurrent software. So what do I mean by cancel? Cancel is the deliberate premature termination of a task, and a task is a unit of concurrent execution. And I'll talk more about what we mean by that later. I also argue that cancellation enables important system trends, one trend being increasing complexity. So cancel facilitates coordination of tasks. It allows the system to stop and reorder work and pursue more diverse work strategies. Another trend is resource usage. Jobs are getting more expensive. And cancel enables efficiency by reducing resources spent on wasted work. And lastly, increasing usability demands, giving users choice on what to do. And cancel gives users the ability to stop work when they want. So there is some support for canceling tasks in existing languages. So here we can see some common task constructs in Java, C#, and Go. A thread in Java, a task in C#, and a Go routine. And languages also have these ways to cancel tasks. For example, in Java, you can call interrupt on a thread. And C# provides something called a cancellation token, and Go provides something similar. So I'll jump a little bit into examples of how these work. When you interrupt a thread, a flag is set on the thread, and code executing anywhere on the thread can check that flag. So for example, in this foo function, it's checking whether the flag has been set. And it can decide at that point to stop, or it can throw an exception and allow the caller to handle it. So we see here a caller. This caller calls foo, and if foo is interrupted during its execution, it will throw that exception, and the caller can perhaps stop and clean up and do whatever it needs to do. And you can interrupt threads very easily just calling interrupt. Cancellation token is slightly different. Unlike interrupt, which is thread global, a cancellation token is typically local and is passed as a parameter. So you can see here a function calls bar and it passes the token along. And a function can also check, like interrupt, if it's been canceled and do whatever work it needs to do. And you can cancel via something called a token source. I'd also like to point out that support is emerging in other languages. In C++ 20, a stop token has been introduced, and it shares some design elements. So anecdotally, implementing cancel is difficult. You can see here some of these comments. Cancel can't be supported, it breaks. Not clear understanding of how to do it. And some of these posts have been viewed you can see 20,000, 150,000 times. So it isn't surprising that buggy cancel can lead to software failures. You can see a few examples here, data loss, corruption, resource leaks. So we think now is a good time to study cancel. Cancel is important to software. Cancel is difficult and problematic. And so far, systematic research into this functionality has been somewhat limited. So let me talk a little bit about what we've done. So our primary goal with this work is to develop an initial understanding of how cancel is used in systems and what are the associated problems. It's primarily an empirical analysis. So we set out to answer these three questions. Firstly, why are tasks canceled? And we looked at feature requests. Secondly, what are the sources of problems? And we looked at reported issues. And finally, how to detect some of these problems. And we identified some anti-patterns. And you can see some numbers here, 60 feature requests, 150 issues, a number of anti-patterns, and some of the applications that we looked at on the right side. So I'll talk a little bit about our findings. Firstly, I'll talk about the reasons why cancel is requested in systems. And we find that there are three major reasons. One reason is efficiency. A task doesn't produce useful results. An example comes from Spark. Redundant or speculative task executions aren't needed anymore after a stage completes. Another reason is flexibility, giving users the ability to stop a task for whatever reason. And we can see an example is the ability to cancel a long-running query. Finally, priority. And this is when a more important task needs to be run. An example here from HDFS is that a checkpointing task is canceled, so a failover task can proceed. I'll quickly point out just some other details. Firstly, among these requests, bulk cancellation is rare. So in general, cancel issuance is fine-grained and it requires thoughtful targeting. And secondly, many of these events are expected and occur with some regularity. So they're part of normal operation. So I'll talk now about some of the problems that we've seen in cancel. So our first challenge is how do you divide these problems into a general categorization? And we find that these problems best fit into three phases. First is what we call cancel initiation, deciding to cancel a task. Secondly is signaling, propagating a signal from the initiator to a target. And finally, fulfillment, actually ceasing the execution and cleaning up partial work. And we actually find that in our 150 issues, the bugs are equally spread across these three phases of cancel, which suggests that each phase of implementation has its own challenges. And I'll give some examples of problems now that occur in each of these phases. So in cancel initiation, one type of problem is where a dependent task is not canceled, but it should be. We call this overlooking triggers. And this example is from Rosalind. And here, a compilation task is stopped prematurely, but the dependent task, an analyzer, keeps executing. And this leads to resource leaks associated with the analyzer. And in this case, the relationship is not directly parent-child, but the analyzer consumes events emitted by the compilation task. Some other initiation problems, a triggering event is not detected correctly, or cancel is overused. And you can look at some of these details in our paper. And we also consider how to tackle these problems. So in initiation, many of the problems relate to identifying dependencies. Simple dependencies like parent-child can be identified through code patterns. And we look at that in the anti-pattern section. But even semantic dependencies, they share key data that can be identified and tracked. So the example we just saw, the compilation task and the analysis task, they shared an event queue. So now I'll talk about some signaling problems. And one type of problem in this category is that a signal is dropped on its way between being issued and being handled by the target. So I'll give an example. And this example is probably familiar to Java developers. So here we see some code that's similar to what I mentioned earlier. A function does some work, and maybe one of the callees throws an interrupted exception, and here it might not do anything, right? It might rely on the caller to clean up and stop. And so let's look at the caller, and it indeed does that. Checks the flag and it cleans up, so that's okay. But if the bar function uses a library method like sleep, and it's interrupted during that, the default behavior of many Java library methods is actually to unset the signal. Because bar doesn't do anything, the run method will not know that it's been canceled. It will not clean up its work. And the fix here is to reset the signal. So you might ask, does this problem occur in other languages, like token cancellation? And it does in a different way. So here you can see again an example similar to what we saw before. A foo method has a token, and it can check if it's canceled. But in many cases, foo wants to be able to support execution without a token, so it makes the parameter optional. It's quite common. The challenge is that if you see in this run method, it has a token available in its context, but it doesn't pass the token to foo. And so the burden is on the implementer to make sure that it's doing all this work correctly. And if it doesn't do that, then the cancel token. The default cancel token will be used, which will never return that it's been canceled, and stop and cleanup will not take effect. So that issue is a little bit simple. I mean, here is something a little more challenging. Sometimes you have multiple tokens available in a given context. This might be because there are many sources of cancellation, a user event or a system event. And it's unclear in some cases, which token should be used. Should one of them be passed? Should both of them be passed? And this is kind of a heavy burden on an implementer. It might require investigation into what the source might be and what the downstream behavior might be. So how do we tackle these problems? Some of the simple problems can be done via antipatterns, and we talk about that later. But some cases are more complex, like having multiple sources in a given context. Sometimes a drop of a signal is intentional, and sometimes these signals are wrapped. Another category of signaling problems is what we call untimely delivery, and you can read more about that in our paper. So last, I'll talk about fulfillment problems. And this problem relates to cleaning up partial work. Unsurprisingly, cleanup is complex and a source of many problems. So let me give a couple examples of defective cleanup. One is that cleanup is incomplete. So here you can see a task make some updates to system state, and then it checks if it's canceled, and it reverts those changes. But here, maybe it missed one of those changes, and in this case, it led to a corrupted system state. Another problem is if cleanup is incorrect. So an example here, system makes an update to a write log, and it might check if it's interrupted, and it reverts its update. But the implementer actually used the wrong API. And in this case, from Solar, it led to a data loss problem. And maybe the right method is undue. So incorrect and incomplete cleanup are the majority of cleanup issues that we've seen. Cleanup may be ordered incorrectly and may be missing. So how to tackle these problems? This is a little bit more challenging. Missing cleanup can often be detected automatically, but incomplete and incorrect cleanup, is tough. It might need more language support or developer tools. So lastly, I'll talk a little bit about antipatterns. So looking at these issues, we discovered a few common antipatterns that suggest broken behavior. One example is here. So inside a Java method, it has a catch block, but it leaves it empty, which is common, as we saw before. But the fact that it's inside a while loop, makes it problematic. Because if a cancel is issued to this task, the cancel may be delayed indefinitely. And this relates to bugs that we've seen in the signaling and fulfillment stages. A similar example is seen in C#. So a token exists in a context, but it's never checked, and it's never passed subsequently. And it's done inside a while loop, which makes it especially problematic. Some other anti-patterns that are in our paper. One is misuse of the interrupt API in Java. Another is when a child task is not canceled, and it should be. And another case relating to token is a token is not passed. So these checkers, or these anti-patterns, we built checkers on a tool called CodeQL. It's a platform for static analysis, supports Java, C#, other languages. And the anti-patterns are relatively easy to write. In this case, just tens of lines of code. Here are some of the results. You can see that the anti-patterns that we've detected are spread across a number of applications. So in summary, cancel is an important functionality, but it's difficult to implement and it's problematic. So far, research in this area has been limited, And we've tried to begin by classifying use cases and problems. And we hope this can help develop better approaches to cancel implementations, whether through language features, programming models, developer tools, or detection tools. And that's it.